Welcome everybody to the Enterprise Concerns track. This will be the Virtualization Under Attack Breaking Out of KVM talk with your speaker, Nelson Elhaj.
All right, good morning everyone. Hope you're all recovered from partying last night. All right, I'm going to be talking about attacking and breaking out of the KVM, the Linux kernel virtual machine virtualization system or hypervisor. I assume that you're vaguely familiar with what KVM is if you're here, but it's a open source virtualization solution for Linux that was the first virtualization solution to sort of be primarily developed in tree and officially blessed by the upstream Linux developers. And it's basically becoming the new hotness for doing virtualization on Linux, and it's become the official platform for Ubuntu and Red Hat, although they also still support Zen. And a couple words about who I am before we jump in as well. I'm a kernel engineer at a company called Ksplice, which has nothing to do with virtualization. We were just acquired by Oracle. But in my spare time, I hack on all kinds of open source security stuff, primarily Linux kernel, but I've recently branched out to do work into KVM, which is what I'm talking about today. So brief overview of what it is I'll be covering today. We're going to start with a fairly high-level overview of how KVM works, how it's structured, what the different components that go into it are, how they play together, with a focus on looking at what the attack surface is here. If I'm an attacker who is trying to break out of KVM or otherwise cause trouble using KVM, which of these pieces should I be particularly interested in? Then we're going to dive into a case study of a working breakout exploit that goes from code execution in a KVM guest to getting execution on the host. We'll look at the bug that I'll be using, and then we'll do a pretty deep technical dive into the exploit, understand how it works, understand some of the problems and solutions that come up when you're looking at exploiting KVM. And we'll talk about, and then once we're done, we'll talk about some conclusions that I think are suggested by this work, some further research that I'm planning on looking into or that I would love to see other people look into. And then finally, we'll finish with a demo of Virtunoid, my exploit against KVM, because no exploit talk is done without a demo. All right, so let's start with the architecture overview. So there are three main pieces that go into making the whole KVM system work that let you actually booting a virtual machine. There's kvm.ko, the main kernel module. There's kvm Intel and kvm AMD.ko, implement the hardware support for Intel and AMD respectively. They're different flavors of hardware virtualization. And then there's the user space driver, QEMU-KVM, which is the final component that is sort of independent from the rest. It's developed in parallel, but not maintained in the Linux tree like the rest. So kvm.ko is the core piece of in-kernel code that lives in Linux 2.6.git, etc. It is the main kernel driver. It provides the interface for a user space driver to create a new virtual machine, allocate virtual CPUs, control memory mappings, etc. It's mainly concerned with emulating the CPU and the memory management unit, the core processor, using the hardware virtualization extensions. Although it does also emulate a few hardware devices directly in kernel for efficiency, so that you don't have to call out to user space. And then one of my favorite pieces of trivia about this kernel module is that even though it uses the hardware virtualization extensions, and so most of the CPU emulation is provided by the hardware, it actually contains a full x86 emulator because it turns out that you still need one to handle a few edge cases. And so that's sort of an excellent piece of hairy code for anyone who's looking at attacks. And then the other part of the in-kernel component is just the hardware-specific. AMD and Intel have different sets of virtualization extensions that work broadly similarly but are completely different in all the details. And so there's one driver each and one kernel module each to interface with those. They're relatively hairy, but they're fairly small pieces of code. They're just one C file each, 4,000 or so lines of C. And then finally, we come to QEMU KVM, which is the user interface, the user space driver. It's a fork of the classic QEMU CPU emulator, although I think it's now been mostly or entirely merged back into the QEMU tree. And it is responsible for the user interface, the sort of the main run loop, and implementing all of the virtual devices that your VM needs. Because obviously in a virtual machine, it's not just a CPU and a memory manager and some memory. It needs to have a virtual hard disk, a virtual clock, virtual network driver, all that goodness in order to actually do anything useful with your machine. And QEMU KVM implements a huge number of types of devices. And even though most of them aren't active in any VM, even if you just look at the code that is active in running a typical virtual machine, I think there's an order of magnitude more code here than there is in the kernel module, because devices are hairy. There is a work in progress to replace this with a separate user space driver that will also be maintained in the Linux kernel tree. But that work is quite a ways out. It's still in a very early stage of development, and I think it'll be years before, certainly it'll be years before it's the main thing that people are using. So if we're thinking about KVM security today, QEMU KVM is the user space component. So now we'll run back, again look at those, this with more of an eye for attack surface. KVM.ko for someone trying to break out of the guest is a very tempting target because it runs in the kernel. So so if you successfully exploit this from the guest, you get ring 0, fully privileged escalation on the host with no further work on your part. But there's not much code here comparatively, and much of that code is actually dedicated to talking to the host's user space, not directly to the guest. And so the amount of attack surface here is comparatively small. But again, it is very high value attack surface. And that x86 emulator that I mentioned, x86 is a hairy instruction set. And so that's a bunch of complicated code that's only executed in edge cases, and so it doesn't get a huge amount of testing. So that's a very interesting target. There have been a number of bugs discovered where by causing it to incorrectly emulate x86 code, you could actually get privilege escalation within the guest, which is not the same as what we're talking about, but is also interesting. I won't be focusing on that in this target, but it's a very interesting target that I hope to go after in the future. KVM Intel and KVM AMD are relatively boring from an attack perspective. They're sort of mostly straight-line code that deals with mapping between the hardware's idea of the state and the main KVM world's idea of the state. But there's also a lot of subtlety there, and the hardware virtualization extensions are extremely complex. And so I won't rule out at all the possibility that there are subtle problems in the mapping of that state to the hardware that could lead to interesting attacks. But it's not the first place I would look. And then finally, we come to QEMU KVM here. And this is just a goldmine of targets. There's hundreds of thousands of lines of code here. Most of this code comes from QEMU, which was largely written by one guy, Fabrice Bellard, who is an absolutely brilliant hacker, but he's sort of one guy working more or less in isolation, building this thing, can only accomplish so much. You're going to make mistakes. It hasn't had a huge amount of peer review. It hasn't had a huge number of people looking at it. Although now that it's become more high profile with KVM, it is getting more attention. And all of those emulated devices that I talked about, they interface directly with the guest. They're parsing I/O requests or memory requests from the guest. And we all know that parsing code is sort of your first place to look. One feature that is worth knowing about this is that this is a user space program, and furthermore, it's often sandboxed by SE Linux or AppArmor or something similar. And so a successful exploit against QEMU KVM will require a second privilege escalation potentially to get full access to the host. But fortunately, Linux never has privilege escalation attacks, so it's pretty much a theoretical concern. All right, and this is in fact what I'll be talking about for my attack today. So now that we've got a sense of how all these pieces fit together, we're going to dive a little bit more into a bug that I found in QEMU KVM that we're going to be using to break out of the guest. So this bug was CVE 2011-1751. I've quoted here the text from the Red Hat security advisory about this. And it was found that the PIX4 power management emulation layer did not properly check for hot plug eligibility. All right, what does that mean? All right, well, so PIX4 was a Southbridge chip. It was an actual chip that was used in a lot of Intel chipsets around 2000 or so. And it's the default Southbridge emulated by QEMU KVM. And so since it's the Southbridge, most of the interesting buses and devices in QEMU hang off of it, including the ACP support, the PCI bus, a PCI ISA bridge. There's an embedded real-time clock, all kinds of goodness there. So PIX4 supports PCI hot plug. On a real machine, you'd use this to electrically disconnect a PCI card so that it could be safely removed. In a virtual context, the hot plugging a device means that you disconnect that device from all of the I/O buses that it's connected to, and then you just free the memory backing it. In QEMU KVM, there's this qdev free call that's supposed to go and free a QEMU device, call the cleanup function and free it. But a lot of devices in the QEMU implementation weren't implemented with hot plug in mind. For example, why would you hot plug the real-time clock on your motherboard? That's not a thing that you expect to be able to do. But it turns out that there were insufficient checks when you wrote values to this PCI hot plug port. It wouldn't check that the device you were trying to hot plug actually was supposed to be hot pluggable, was supposed to be ejectable. And so it would just go and free it. And in particular, one thing that you should not be able to free is the ISA bridge. How many people here actually remember physical ISA cards even? All right, good, most of you. But obviously we don't have those anymore, but there's still a virtual ISA bridge in the Southbridge on still basically all PC chipsets. And so that doesn't make any sense to hot plug, because it's not a physical piece of hardware. And so QEMU emulating that also, why would we hot plug that? They didn't anticipate that, but the software lets you hot plug it. And in particular, the thing that I'll be looking at that goes wrong is the real-time clock hangs off the ISA bridge. So when you hot plug the ISA bridge, you free the memory backing this real-time clock. But the real-time clock doesn't clean up after itself, and it leaves around some timer objects that we'll be talking about. So we've thrown up our first bit of code. So there's this QEMU timer struct is used by the QEMU system to maintain timers. If devices want to say, wake me up in 1 second, they register a timer that has a callback and an opaque pointer to call the callback with. The real-time clock obviously cares about timekeeping, so it uses a timer device to ask the host to wake it up once a second and say, all right, time to advance the real-time clock to the next second. But if I unplug the virtual real-time clock, that frees the memory backing the real-time clock, but its destructor doesn't clean up any of the timers that it uses. And so we're left with this timer that says, in 1 second, call a function on that real-time clock object. But that real-time clock object doesn't exist anymore, and so we have a classic use after free. And so within a second, at the next second boundary, we're going to call this RTC update second, which updates the real-time clock, on a freed object. And as you can tell, probably nothing good happens. One hilarious thing about this bug is how simple it is to trigger. That piece of code, if you run it on a vulnerable version of QEMU or KVM, you'll get a seg fault. And this bug was actually found by a trivial fuzzer I wrote that just wrote literally random values out random I/O ports. And sooner or later, it happened to stumble on that pair of values, and I got a seg fault. All right. So we understand the bug. Let's dive into how do we go from this use after free to getting code execution in the host. We're going to talk about 3 components of this exploit. First off, the basics of I have this use after free. How do I go from there to controlling RIP, controlling the program counter? And once I have the program counter control, how do I go from there to actually executing my shellcode? And then finally, I will have, for the purposes of that, I'm going to be assuming that I can guess certain addresses in the host, that there's no address space randomization. And then we'll talk a little bit more about some of the tricks that I had to do to bypass address space randomization and make this actually completely work on a completely vanilla KVM install with no twiddling, no disabling of security concerns. All right. So the high-level to-do for getting RIP control. So we're going to inject somehow a fake QEMU timer into the QEMU KVM address space. We're going to create a timer object that we control at a known address inside the KVM process. Then we're going to eject the ISA bridge with that one out instruction I showed. And then we're going to force an allocation over the freed RTC state where we control the second timer pointer to point at our timer. So then within 1 second, RTC update second will now run on this RTC state that's been replaced by our data. It will update the fake time in our fake RTC. We don't care about that. But then it will reschedule the second timer to run again in 1 second. But we've hijacked that pointer to point at our timer. So 1 second later, it will call that CB member, the callback, in our timer, and we'll have RIP. So there's two interesting parts here. One, injecting data into the QEMU process so that we can create this fake structure. And two, forcing a controlled allocation of a controlled size and contents in the QEMU process. So when it comes to injecting fake objects into KVM, this is actually one place where we have a easier job with virtualization in some ways than we might otherwise. The way that QEMU KVM works is that the physical memory in the guest is just backed by a simple mmap in the host. And so if we know the physical address of any object in the guest, and we know the address of that mmap in the host, we just add them together to get the host virtual address. So in fact, we don't have to do anything at all to inject items into the host. We just allocate them, and they're already there in the host, and we just have to do some arithmetic to figure out what the address is. And for now, like I mentioned, we're just going to assume that we know the address that mmapped region is at. If there's no ASLR, this is a realistic assumption. It's very predictable. If there is address space randomization, we'll get to that later. All right, so creating fake objects, fake structures to play around with in the host is very easy. Cool. All right, now in order to force allocations in the host, because we also need to get the host to do a malloc of a controlled size with controlled contents to overwrite that now free region where the RTC state used to live, we're going to use a feature of the QEMU network stack. QEMU contains a user space virtual network stack that can be used to give your guests network without any special privilege, without needing bridge devices or ton tap or any of that crap. So this works by implementing a whole virtual LAN inside the QEMU KVM process, including a DHCP server and a NAT that gives you a NAT gateway to access to the outside world, a DNS server, etc. And this is the default network setting for KVM, so assuming that we're relying on it is not a totally unreasonable assumption. Although in more heavyweight assumptions, we might just be using more heavyweight environments, we might be using the bridge network device, and we would have to try something different. But this is a reasonable place to start. So this virtual LAN, by default, delivers packets synchronously. If the guest injects a packet onto the virtual LAN, it doesn't get queued anywhere. The VM just immediately goes and looks up and says, all right, that IP address is that virtual host, and just calls the method associated with receiving packets on that virtual host. But if a packet is delivered while the system is in the process of delivering a first packet, in order to prevent infinite recursion as the stack keeps growing as it delivers packets, it queues the packet onto a queue by mallocking memory for it and copying its contents into there. So that's a malloc that is just of the packet plus some header data. So it's if we controlled that packet, it's almost completely controlled, including length and data. But what we need is a way to generate a packet in response to a packet that we send. So what we need is a virtual network service that we can send a packet to that will, in response, send back a packet that has the same or almost exactly the same contents. Does that sound familiar? The virtual network gateway responds to ICMP ping, responds synchronously to ICMP ping packets. So in order to force an allocation in the host, all we have to do is get the data that we want, minus a brief header that we don't control, and send it to the virtual gateway as an ICMP ping packet. The gateway will reflect that packet back at us. The network stack will detect that there's recursive packets going on. It will do a malloc and queue it. And so we have a controlled allocation of controlled contents and controlled size, exactly what we need to exploit this use after free. So putting it together, we allocate that fake QEMU timer. We point the callback method at whatever RIP we want to get this process to jump to. We calculate its address in the host using that arithmetic that I showed earlier. We write the value 2 out that I/O port to eject the world and free all this memory. And then we ping the virtual gateway with ICMP ping packets that contain our fake RTC struct as fast as we can and hope that one of them ends up in the memory that the RTC state used to allocate. And it turns out that this basically always works. All right. So we've got control of the instruction pointer. We can make this thing jump to any address that we want. That's cool. What now? Well, let's go over some options that I considered. We could set EIP equals 41414141 and declare that the rest is trivial. I could disable NX in my laptop's BIOS and be like, all right, I'm just going to jump to some shellcode. That's a demo. Getting more interesting, I could do a standard ROP pivot, pivot the stack pointer to data that I control and do a ROP sequence to do a mmap or an mprotect or something, and get an executable buffer there, copy my shellcode in, do that whole deal. But I don't really like ROP. Or I could do something else kind of clever that I'll talk about that takes advantage of QEMU's own infrastructure to turn it against itself in kind of a cute way. That I think, in this case, has some advantages over the standard ROP technique, and I'll talk about that. So let's take another look at the QEMU timer struct that we're faking. Because remember, we're not just causing a jump to an arbitrary EIP. We actually control a whole fake QEMU timer structure. And if we look at the QEMU timer structure, one field that we find that I didn't mention before is this next field. The way timers actually work is they're stored in a sorted linked list by expiration time. And every time the run loop the QEMU run loop wakes up, it runs these timers, which just consists of it walks this linked list following the arrow next pointer as long as these timers are expired, and it calls their callbacks. So there's no reason to restrict ourselves to faking a single timer object. Remember that we can easily inject as many objects as we want into the host. So we just fake a whole chain of these. One timer points to the next, points to the next. We set their expiration time to 0 so that they're all going to be expired. And then if we set up this sequence here, what that results in is we call f1 of x, f2 of y, f3 of z, and we can chain arbitrary one argument function calls in the host. So it's sort of a similar technique to ROP in that we're reusing fragments of code from the host, but with a slightly different flavor. All right, so one argument function calls are cool, and we could try to do something ROP-like with that. But really what we want to do is call something like mprotect, which we need a couple of arguments. So to expand calling functions with several arguments in the host, we're going to need a little bit more cleverness. We're going to have to learn a little bit about the AMD64 calling convention. AMD64 on Linux, the sysv ABI, we pass arguments in registers for integer and pointer arguments. They go in RSI, RDI, RDX, and then a bunch more, up to 6 of them. But I'm only interested in the first 3 for now. And so every version of QEMU run timers that I've looked at as compiled by GCC leaves RSI untouched. I think I got that backwards. The arguments are actually RDI, then RSI. But so it leaves RSI, the register for the second argument to a function call, untouched. So that means that if we can find a function or a gadget that looks like this hypothetical set RSI gadget that mobs RDI into RSI, and then what we do is we set our first function to call set RSI, and then that means that RSI will get set to that x value, the first argument that we provided, populating the RSI register, and then the second function call, f2, will be with two arguments that we control, y and x, from my diagram earlier. All right, that same trick unfortunately doesn't work with RDX because the compiled code for that QEMU runtimers loop tramples over RDX. So we can't control the third argument register in the same way. But what we can do is, find another function that somehow takes some structures as an argument, as the first two arguments, unpacks those, and does a 3-argument function call based on those. So let's see what we do here. So this unlikely looking function is my set RSI gadget. So if we look at this, what this is going to do, so this is the function that's used to write to an I/O port on the host. So if we call this with some argument as the first argument, it's going to turn around and copy that into RSI because it's using it as the second argument. And so then, assuming that we can find some value of adder that makes the I/O port write function not clobber RSI, the net result of running this code is going to be that we'll move RDI, the first argument register, into RSI, the second argument register, and then write to an I/O port. And hopefully we can find an I/O port that we don't mind writing to, because most I/O ports, writing to them once is relatively benign. For getting to mprotect, we're going to use this function that I found, this I/O port readdl thunk. So mprotect is a 3-argument function that we need to call with an address, a length, and a protection flag. We want to call it with protections of at least prot exec. We would prefer prot exec or prot read, but prot exec suffices. And so this cute little function takes a pointer, which is a pointer to an I/O port, I/O range structure, follows some pointers from that, and calls a function pointer on the I/O port with some value that's controlled by the second argument and that I/O port structure, and the value 4, which conveniently happens to be equal to prot exec. So what we're going to do is we're going to construct a fake I/O range structure and a fake I/O range ops structure such that when we call this, it's going to call mprotect on our I/O port with, some reasonable value and prot exec. And then the fourth argument will just be ignored because mprotect isn't expecting it. So we allocate that fake structure. We allocate this I/O range. We make sure to make it page-aligned because mprotect requires page-aligned arguments. We point its ops struct at our fake ops, and we set the base to minus page size because we're going to subtract off the base. We call CPU out L with 0 to set RSI to 0. We call this readdl thunk function does an mprotect on our fake structure, and then that does an mprotect of that whole page to be executable. We copy our shellcode immediately after this dummy structure, and we jump there. We have full shellcode execution. All right. And why? I mentioned that I have some reasons for preferring this technique to ROP, the standard return-oriented programming technique that would have worked just as well here. One thing that I like about this is that continuing execution, causing KVM to not crash, is dead simple, because in some sense we're not even corrupting anything. We're just constructing legitimate timer objects and feeding them to the QEMU main loop. So we're not smashing the stack. There's very little corruption to clean up. Another feature that I like is that we reduce the dependence on the details of how the code is compiled. All I've shown you basically has been source. There's very little assembly. And so this technique, exploits written with this technique, should be very portable across different builds of KVM, which is very important if we're trying to attack something on Linux, because every vendor has a different build with slightly different compiler flags, a slightly different compiler version, and releases updates fairly frequently. And so if I have to do the full ROP thing for every single binary out there, it's a bit of a pain, whereas this just requires that I have a symbol table for every binary out there. And finally, I'm just honestly not all that good at ROP, and I don't know of great tools for doing it automatically on Linux, and I didn't want to deal with that. I wanted a technique where I could read source, not assembly. All right, so I have been making, though, the assumption that I know where addresses in the guest live. In particular, there's two addresses that I need. There's the base address of the QEMU KVM binary in memory to find out those snippets of code that I'm reusing. And then there's that physmem base variable that I referred to, which is the address of the physical memory mapping inside the QEMU KVM process, so that I can know where my fake structures that I'm injecting are going to live. So option A is to find a sufficiently powerful information leak that I can leak out all of those addresses and just win. That's a standard technique. Option B, if I don't want to find an information leak, is we're going to assume that our KVM binary is compiled non-PIE, non-position independent. This means that while the stack and the heap and the mmap region and all that are randomized, the actual binary itself is loaded at a fixed address. This is a reasonable assumption because as of today, every distribution out there ships a non-PIE KVM, except for maybe hardened Gentoo or something, but I just don't care about those guys right now. So that means that we know where the code addresses are, and we know where any static data, .ro data, .data, .bss inside the process, we know those addresses for a fixed binary. So we're going to use another arcane feature of the KVM emulator, the FWCFG for firmware config subsystem. This is a system that lives behind two emulated I/O ports that you're not expected to know or care about. It's sort of a backdoor for KVM to communicate with the KVM BIOS, because the BIOS obviously needs to know a whole bunch of details about the hardware, like the ACP tables, the E820 map that shows it which regions of memory are legal or not. And so this provides an interface for the BIOS to read and write various tables from the host. It supports exporting writable tables to the BIOS, so that the BIOS can blat some information into the host for the host to use. It turns out that as of today, the source code of, if you look at the whole source code of QEMU KVM, there actually isn't any code that exports a writable table, but the firmware config subsystem as of today, and I've reported this bug, but it hasn't been fixed yet, doesn't check if the table that you're trying to write to is supposed to be writable. So the BIOS can just go in and scribble over the memory allocated for the E820 map in the host. And several of regions, such as the E820 map, are just a statically allocated buffer in the host, which means that they're at a fixed address in PIE, and they're writable from the guest via those I/O ports. So we get up to about 500 bytes of writable data located in static variables at a fixed address in the host. And so that's data that we can control and whose address we can predict. We can't just port our entire attack over to this space because I need a page-aligned address for mprotect, and those structures aren't guaranteed to be page-aligned. But so what I can do is I can construct similar fake timer chains in there to build a read4 primitive that lets me read out 4 arbitrary bytes of the address space, basically build an info leak out of that. Use that to chase pointers to find that physmem base address that I was looking for, and then once I have that, I can proceed as before. The one other detail that we need here is now, instead of constructing a single timer chain and jumping to it, we're actually going to do that multiple times. And the way we're going to do that is previously I showed that timer chain that I constructed ended with arrow next equals null. So just basically, this is the end of the timer chain, stop here. Instead, now I'm going to end them with a timer object that calls back into our good friend RTC update second, which is going to do some updating of the real-time clock that I don't care about, and then it's going to re-register that timer to run in 1 second and return. So this means that I construct this timer chain that does a read for and stores the address somewhere that the guest can see it, and then we return to the QEMU main loop, return to the guest. The guest does some computation based on the results of that read, and then hijacks the timer chain again, because there's now a timer that we control that's being called once a second inside the host. And so that there is enough to get us to a fully weaponizable, fully functional ASLR and NX bypass exploit against a stock KVM build on a modern Ubuntu distribution. Anyone have any quick questions about the exploit before I proceed to some of my thoughts and conclusions and do the demo? All right. So I guess some of the conclusions that I want to draw from this, and I want you to draw from, is that VM breakouts aren't magic. A lot of people, I think, assume that virtual machines are sort of automatically this crazy security layer that, breaking them out, you'd have to be some crazy hardware wizard to figure out like how this virtualization works and get by or something. But they're just code. They're even just a bunch of user space C code emulating a bunch of hairy devices. They're just as vulnerable as anything else. Honestly, as of today, I would personally much rather try to be tasked with writing a VM breakout than with trying to break out of, say, Chrome. So actually, they are another isolation layer. They do give you security, but they're not actually a particularly strong one compared to any other isolation layer. They're just more software. They work just like anything else. And as always, the device drivers here are the weak spot. The emulated device drivers in your host are tons of code emulating hairy devices speaking bizarre arcane protocols. And that's where you're going to find your bugs. And if we look at some past breakout attacks, a couple of Invisible Things Lab in 2008 published this paper called Adventures with a Certain Zen Vulnerability, where they took a Zen bug and showed how to weaponize that into a full escape. That was a simple integer overflow in the Zen virtual frame buffer, classic bug type. They did some of the similar techniques that I do, ROP, ret to libc, get nemprotect, etc. Cloud Immunity at BlackHat 2009 released an exploit called Cloudburst, which was a VMware breakout. That was a bug in missing bounds checking in the VMware virtual SVGA card. Again, classic bug class, classic techniques, totally trivial, comparatively. And then another interesting bug that I wanted to mention was that Invisible Things this year released a paper called Software Attacks Against Intel VTD Technology that described how you could use software in conjunction with a non-malicious hardware device that was passed through the VM to break out of a Zen guest in violation of Intel's hardware IOMMU stuff. It was interesting for a couple of reasons. One is that it was sort of an attack against some of the underlying hardware primitives. It's sort of the kind of attack I had in mind when I was talking about the KVM AMD and KVM Intel modules. That's where you would look to think about attacks that had to do with the software using the hardware incorrectly. But then the other interesting thing was, even though it started out as this super arcane, obscure hardware attack, the primitive that they actually got out of that hardware attack was a memory corruption bug in the host. And then they did the whole usual stack of scribbling over data, overwriting function pointers, et cetera, the whole usual arsenal of memory corruption techniques. And so these VM breakouts are pretty much end up looking like just any other memory corruption technique. They're a little bit tricky to get right, but virtual machines aren't fundamentally harder than anything else today. Some thoughts that this has suggested to me about what we should be doing to make the situation a little better. QEMU KVM absolutely should be sandboxed. If you're deploying KVM in some environment, use a solution that sandboxes the QEMU KVM process as tightly as you can. There's lots of work well underway on this before this talk. Red Hat's virtualization stuff by default sandboxes it into a very restricted SE Linux profile. I believe Ubuntu does something similar. But so absolutely, QEMU KVM has to, if you're running virtualization in a secure context, you have to assume that a determined guest can break into that. And so put as many layers as you can, another layer around that process. An obvious no-brainer to me is that QEMU KVM should be built as PIE. The main reason that people don't build things as PIE is performance reasons, because PIE means you lose a register holding an address base. And on i386, we only have like 6 general purpose registers to start with or so, losing another register hurts a lot. But no one is seriously running KVM as a 32-bit guest today, or as a 32-bit host today. You know, maybe hobbyists for development or whatever, but no one is doing serious deployments. So we can spare that extra register, and making it PIE would mean that I would have had to go and find a serious info leak in order to proceed with this exploit. We could try, there's some crazier things that we could think about that I think the KVM guys have been thinking about that I'm going to ponder about. You know, we could try sort of lazily mapping the guest RAM or something, or isolating device drivers into some kind of lightweight thread that only has access to the portion of the guest RAM that it needs. That's a more major restructuring, but potentially would make exploits like this a lot more of a pain. And then, you know, I made use of a lot of different function pointers at various points. We could consider identifying ones that are particularly likely to be, you know, exploited by the host by a guest attack, and, you know, XOR encoding them or somehow otherwise obfuscating them. Again, a standard technique, but I think it's time that we seriously consider whether KVM could benefit from that, because I think it's only going to become a more high-profile target. And finally, I want to see more people auditing and fuzzing and looking at QEMU KVM, because I really think this is going to become a very high-profile attack target, because, you know, everyone is deploying virtual infrastructure these days, and a lot of people are relying on it for isolation between their virtual machines. And since KVM seems to be the new hotness going forward, everyone's going to be using KVM for that. And so we need to be one step ahead of the attackers on figuring out where our weaknesses are. All right, and some future research directions beyond that are, my next project in this space, I think, is going to be finding some serious time to attack kvm.ko. In particular, that x86 emulator is totally sketchy, and there's got to be hilarious bugs there. Another open question in my mind is, how hard is it to fingerprint the exact version of KVM that a guest is running under? Because I assumed that I know the exact version, the exact, you know, KVM binary that I'm running against to know addresses. So how hard is it from the guest to fingerprint the behavior, or possibly do more exotic things like cache timing attacks to, against the host to figure out exactly what I'm running against? And finally, we need to understand what the common info leak classes are going to be going forward in QEMU KVM. Because once we have things running as PIE, people are going to start looking for info leaks. Is there some equivalent of the Linux kernel's Rosen bug, where there's just dozens of stupid info leaks that we're not aware of, that look trivial, but that a dedicated attacker can use to break ASLR? And I don't know the answer, and I'd like to know the answer, because it would give me a better feeling for how hard KVM is going to be to break out of in the future. All right, so after all of that talking, it's time for demoing this thing. All right, so I have my tree here. I'm going to run my demo. We're booting here a Ubuntu VM under KVM. I'm just going to boot it into an ordinary Ubuntu kernel first. You know, show off. Yep, it's a KVM VM. You know, CPU info shows it's a QEMU virtual CPU. And then the way that I've actually implemented this, this attack is I've actually taken my user space exploit. The exploit is written as user space code, and I've bundled it up into an initrd that basically just contains a shell script that launches my user space code, and I've built a custom kernel that I'm going to run it against. The reason for this is that, like I said, we're hot unplugging the ISA bridge, and there are a lot of random devices that hang off of the ISA bridge, and if we try to use any of them, we're probably going to segfault. So I've built a minimal kernel that's just configured to not use any of those devices. And I've built a minimal initRD that's configured to just as quickly as possible after the reboot go into my exploit code. I don't have to do this, but it makes the exploit much more reliable. And if we look at grub.cfg, I've configured my kernel and initRD there. So now we're going to reboot the guest. And this time at the grub prompt, we're going to select the Virtunoid exploit. Print some status information. It's doing the read. And we pop up a calculator on the host. So calculator is the standard demo program, but I can do anything we want. We have full code execution on the host. And as you can see, the guest kernel is a little bit unhappy because its real-time clock has just gone away. But it's still running and is mostly alive, and we could shut it down cleanly if we want, but I'll just kill it. All right. So I think that gives us a couple minutes left for questions. I can take them now, or you can contact me and look me up at any of these locations. I'll put the updated slides. These slides have changed a bit since the CD on my blog at some point soon. Question over there? Yeah, I do. I do intend to look at other VMMs, and as I mentioned, this bug was discovered by a simplistic fuzzer, and also on my to-do list is to try to turn that fuzzer and point it at other virtual machines. I chose KVM because it's open source and it's based around Linux, which I'm very familiar with, so it was an easy first target, and because I think it's a shame that no one has looked at it seriously yet, because I think it is up and coming and is going to be a big attack surface. But yes, I do intend to try to repeat some of this work on other virtual machines. All right, I'll be loitering around up here for a little bit if you want to come find me. Thank you all for listening.